We're on Unit 8, Chemical Reactions, and this is page 5. We're starting the next topic of balancing chemical equations. This is a topic that sticks with us for a while. This is one of those hands-on, lots of practice kind of topics. So when reactants and products are in the correct ratio, a balanced chemical equation ensures that mass is conserved. This is the purpose of the balanced chemical equation. It's to make sure that our reaction obeys the law of conservation of mass on paper. In reality, it's going to obey the law no matter what. We just need to make sure that on paper or on the computer, it matches reality. So in order to show this ratio, we use a coefficient and we place it in front of a chemical formula. The coefficient is just a number, anything 1 or greater. So here's an example of something that you could see in a chemical equation. 2 nitrogen gases. What this tells us is that 2 nitrogen molecules are present in this reaction. If you look at it from a slightly different way, yes, there are 4 nitrogen atoms, but to be really specific, we have 2 nitrogen molecules. So you'll notice I didn't change the chemical formula of nitrogen. I put a 2 in front of it. Yes, there are 4 nitrogen atoms, but I did not change the subscript. I did not say that I had N4. That's not true. It doesn't exist like that. All you can do if you want to change the amount of a substance is add a coefficient. Can't change chemical formulas. This means you can't change the subscripts in the chemical formulas. So let's look at the Haber process again. This is the chemical reaction that you're going to need to know by memory for this whole unit, and I'm even going to ask you about it in future units. So this needs to stick with you. This is the skeleton equation for the Haber process. N2 parentheses G plus H2 parentheses G yields NH3 parentheses G. Nitrogen gas plus hydrogen gas yields ammonia gas. But this equation doesn't obey the law of conservation of mass. This is the problem we identified earlier. I have 2 nitrogen atoms in the reactants, and I only have 1 in the products. When I look at hydrogen, I have 2 hydrogen atoms in the reactants, and then I have 3 in the products. So it looks like nitrogen is being destroyed. It looks like hydrogen is being created. Neither of those things happen, and nitrogen does not magically turn into hydrogen. So none of those scenarios are possible. Here's what we do. Adding coefficients to balance the equation will fix our problem. So we'll come back to this in a second. I'm going to approach this 2 different ways. So in this paragraph, I'm going to talk strictly about the nitrogens, and then I'm going to start over, and in this paragraph, I'm talking about strictly hydrogen, and then I'll put them together at the very end. So to balance this equation, we have to compare each element individually in the reactants and the products. So when I look at nitrogen, I want to only look at nitrogen. I want to ignore everything else. So for nitrogen, it has 2 atoms in the reactants, and it has 1 atom in the products. So here's what I can't do. I can't change this to make it just N because it exists as a diatomic molecule. It's always going to be N2 when nitrogen is by itself. So I can't reduce the number of nitrogen atoms. And this one's already at 1. It's as low as it could be. But I can increase the number of atoms. I can start adding more. I just can't take things away when I'm as low as I can go. So here's what I can do. I can put a coefficient of 2 in front of the ammonia. And now when I take a look at it, I have 2 nitrogen atoms in the reactants, and now I have 2 nitrogen atoms in the products. The only way to fix this is how I did it, by adding a coefficient. I did not change any formulas. Do not change any formulas. So at this point, I have equal numbers of nitrogen atoms. And so I'm good. The problem has been fixed as far as nitrogen is concerned. So like I said, I'm going to start over. I'm going to look at just the hydrogen by itself next. Hydrogen has 2 atoms in the reactants, and there are 3 hydrogen atoms in the products. So if I were just going to jump straight in here, I might say something like, there's 1.5 of these. But I can't do that. A coefficient has to be a whole number. It's not possible to have 1.5 nitrogen molecules in a reaction. Can't do it. 1.5 molecules is not a possibility. And remember, what we're doing on paper is reflecting reality. When we do something wrong on paper, it doesn't change the way the world works. It just means our paper is wrong. We need our paper to reflect what happens in the real world. In this case, what actually happens in the Haber process. And we never have 1.5 hydrogen molecules. So the answer here is to use the least common multiple. This will give us whole numbers. So the least common multiple is 6. And that's, 2 here, 3 here, multiply them together. I want 6 here, I have 6 here. Least common multiple is 6. So we want 6 hydrogen atoms in the reactants, which means multiplying this by 3. And we want 6 hydrogen atoms in the products, which means multiplying this one by 2. And those will be our coefficients. 3 times 2, that's 6 hydrogens. 2 times 3, there's 6 hydrogens. And if you think back to our nitrogens, we said that 1 of these and 2 of these. So let's double check this thing. You always want to double check at the end. Make sure it's balanced. It's really easy to get an answer. You can put numbers on the page. That doesn't make it a right answer. That doesn't make it reflect reality. Always double check. Never skip the double check. You'll never catch me skipping the double check, and I expect the same out of you. So this quick double check, and there's a couple of ways you can do it. For instance, here's an easy one. So I write my elements that are involved in the reaction. Let's say that the reactants are over here and the products are over here. So let's just say something like this. Normally I would do it right under the arrow, but I'm kind of out of space. So I counted them up. So nitrogens in the reactants, I have 2. In the products, I have 2. So nitrogens are good. Hydrogens, I have 6 in the reactants, and I now have 6 in the products. And so everything's good here. It works out. I have 2 nitrogens on each side. I have 6 hydrogens on each side. Everything is accounted for. This equation is now balanced, and it obeys the law of conservation of mass. I have some steps here for balancing a chemical equation. The steps, they're fairly simple, but like anything in chemistry, it's a lot easier to just do it than it is to read the steps over and over. And so I'm going to go through a few examples here. And the first one came up a while ago. Hydrogen peroxide, and it's actually a liquid. Hydrogen peroxide solution produces water and oxygen gas. This is a reaction that happens all the time. You've probably got a brown bottle of 3% peroxide somewhere in your house, maybe in the bathroom. This reaction is always happening. It is constantly turning from hydrogen peroxide to water and oxygen gas. It's just what happens. It's why peroxide has an expiration date, because after a while, there's no peroxide left. So the first thing, write the skeleton equation. Here it is. That's step 1. Usually step 1 is given to you. Step 2, count the atoms. So kind of like I did on the previous page, here's the way that I do it a lot of times. So right under the arrow, I write all of the elements that are involved in the chemical reaction. In this case, it's just hydrogen and oxygen. And I count them up. So hydrogens, over here I have 2. And on this side I have 2. So the hydrogens are right now balanced, but I'm not going to put a check mark because we're not done yet. And for the oxygens, I have 2 in the reactants, and I have 1, 2, 3 in the products. So the oxygens are wrong. But here's the thing about it. When I start changing the amounts of oxygens, a lot of times I end up messing up the amounts of hydrogens. And so we have to be careful. And remember that when we change one thing, there are effects in other places. And that's where all of this comes in, especially that last thing. Double check your work. So in the last example, we used least common multiple. But in this one, we don't have to. Here's what I know. I know that in the reactants, there is always an even number of oxygens. Always. But in the products, it could be even or odd, because this one only has 1 oxygen. So it could be 3, 4, 5, 6, it could be any number really. And so since this is always an even number, first thing I want to do is make this one an even number. So I'm going to change this to a 2. I'm going to keep score as I go. This means that now I have 4 oxygens on the product side. So we've changed this one. We need to balance these, and I can do that by adding a coefficient of 2 here. Let's not get too far ahead of myself though. Take a look at this. We changed the number of oxygens by adding a coefficient. This coefficient also changed the number of hydrogens. No longer 2, it's now 4. Now back to the oxygen. I can add a coefficient of 2 to make this one 4. So that changes my oxygens to 4, and it also changed my hydrogens to 4. And so it looks like they're balanced here. Well, let's double check, let's make sure. So 2, 4 hydrogens, 4 hydrogens. 2, 4 oxygens, here's 1, 2, 3, 4, and this one is balanced now. When you do these, the way I'm showing you right now is what I would refer to as the trial and error method of balancing equations. You're changing one thing, you're changing the next thing, and you're just kind of trying to get there eventually. There are other methods to balance equations. For instance, you can balance an equation using algebra. That's something that I might teach you after you have some understanding of this. But it never hurts to know 2 methods, especially for the harder chemical equations. Another thing is I don't always write this part down. I can keep track in my head. When the numbers are this small especially, I can count 1, 2, 3, 4 in my head, so can you. So I don't always write this on paper, but I'm doing it in my head. So let's look at my next example, and you've got lots of open space if you want to add it somewhere else. Here's a reaction. So hydrogen gas reacts with oxygen gas to produce water. And usually with this reaction, we're talking about water in gas form, water vapor. H2, hydrogen gas is a diatomic. O2, oxygen gas is a diatomic. H2O. So just so we can see it, I'm going to go through the same method as last time, hydrogens and oxygens. In the reactants, I have 2 hydrogens, I have 2 oxygens. In the products, I have 2 hydrogens, and I have 1 oxygen. So the obvious place to start is here with the oxygens. So I want this to match this, which means a coefficient of 2. That changed my oxygen count to 2 in the products. But it also had the unintended consequence of changing hydrogen. There are now 4 hydrogens. So my oxygen problem is solved, but it's created a hydrogen problem. So I've got 2 in the reactants, 4 in the products. The easiest thing to do here is to add a coefficient of 2. And that multiplies 2 times 2, and now I have 4 hydrogens. According to my little scoreboard, everything is balanced. Quick double check. 2 times 2 is 4. 2 times 2 is 4. 2 oxygens, 2 oxygens, and we're balanced. As we go along, I'm going to give you more examples. I only gave you 2 here, but we're about to start talking about types of chemical reactions. With every type of chemical reactions, I am going to put in 1 or 2 chemical equations, and we're going to go through the process. So we are going to refine this skill as we proceed through the unit so that we don't have to stay in this one spot for very long.